The third lecture is measurement of unknown impedance. In microwave technology, the fundamental three measurements are there, because if you want to know, as I said, that power is a fundamental quantity, also any AC signal description, the basic fundamental quantity is power. So, you should know how to measure power. Also, you should know how to measure frequency, and also, as I said, that impedance is a very important thing, because by impedance actually you see both in low frequency and high frequency, this impedance characterizes the network. It is a network does not get characterized by its voltage excitation or its current response, etc., but the ratio of that means whatever may be your response or whatever may be your excitation, the characteristic of the network is inbuilt in its impedance. That is why impedance plays such a major role in electronics, and we have again said that amongst electronics engineers, RF engineers are very careful about impedance for impedance matching and having the optimum power delivery. So, these three measurements are necessary for understanding what is happening in any RF RF circuit, and this can be done by a single set of apparatus called microwave bench. So, microwave bench can measure these three quantities. So, however, that is a laboratory component, but here we will be seeing only impedance measurement thing today, because we consider this is the most important amongst the others, because unless and until you know how to measure impedance, an RF engineer will find problem in his career. This is a typical microwave bench. I think all of you have seen it in your thing. You can see the leftmost side, there is a, this is a klystron source based microwave bench. Generally in laboratories you can have a klystron, which is a vacuum tube. It is a very stable tube for giving you some milliwatts of power that is required in the, to do these experiments. But there is also a semiconductor counterpart of that, which is called Gunn diode, whose power level or power output is a bit low, but you know, compared to a vacuum tube, semiconductor is more rugged, that is why that also is used. So, here you can see the left that black one with something that is a klystron source. After the source there is an isolator. The source needs to be isolated, because any source is a low impedance thing. Now, if any reflected wave comes, then you know that sometimes depending on the impedance level of the load, you can have a power, you can suddenly, if you have a sizable amount of reflection, lot of power can come to the source, and being a low impedance device, it can be destroyed. So, isolator is a preventive thing for this. Then after that there is a attenuator. You can see that attenuator is for changing the level of the power level of the whatever is flowing from the source, that you can put attenuation. Then you can see there is a cylindrical thing that is called a cylindrical microwave cavity. It is a frequency meter, where reaction type wave meter also it is called. So, there are some graduations on the cylindrical body, and that is the your frequencies are read there. This is a mechanical way of reading the frequency, but then we pass that to a waveguide section, a rectangular waveguide, which is a basic transport mechanism in high frequency, particularly in the gigahertz range. And if you have sizable power, waveguide is the mode, not a coaxial transmission line. So, in microwave generally the fundamental transport mechanism is through waveguide. So, that is why there is a waveguide with a slot cut at the central portion of that, through which a probe is inserted, and that probe, which is a basically point contact diode probe, that probe is connected to a meter. This is a new thing, this is called VSWR meter. So, there are two meters, two boxes you are seeing. The right one is the meter where you see the waves various parameters, particularly is VSWR, which will come next, and left side is the power supply for that Klystron source. So, functionally this is the that slotted line with carriage, this is that rectangular waveguide I was talking. You can see from the left side it is seen that this is a rectangular waveguide, but that probe that can move over that is why there is a carriage. So, by that you can move it in that slot. So, that means you are on a, you can think of this that on a transmission line you can vary your position of the probe. So, you can sense what is happening along the line. This is the rectangular waveguides thing. Now, there are some components used in the laboratory, these are also required in laboratory. You can see adjustable short, adjustable load, bend ridge guide adapter, instead of our that attenuator, variable attenuator. Then there are two fundamental things are shown here. One is a directional coupler, which is very important. Actually, this is the basis for separating, this device can separate the a forward wave and reflected wave, and this is the basis of modern days replacement of this microwave bench, which is called network analyzer. And then you can also see a magic T. There is nothing magic, but it is a wonderful device. It can act as a power divider, it can act as a combiner, it can act as a summer, it can act as a differentiator all in one. Now, this is a Gunn based bench, as I was saying that instead of Klystron, if you have Gunn, you can this. But basically, if you look at that, you can see this slide, that same thing what we have pictorially shown, the same thing. Actually, there is an RF source, but we are detecting that RF source with a diode, as I said, point contact diode. So, which is on the carriage. So, the diode cannot detect your microwave, but it can detect a 1 kilohertz signal. So, we give a 1 kilohertz modulating signal to the RF, and that is why it comes in with a modulation of 1 kilohertz. The diode can detect that 1 kilohertz and gives you the thing. So, here we have shown which are the RF sections, where is the 1 kilohertz thing, and you see the waveforms. So, you have the RF thing coming from the Klystron at the right. Then after that, after modulation, that same RF waveform looks like the next one. You see that it is having some on off modulation of frequency 1 kilohertz. So, it becomes the second waveform that is shown, and then after attenuation it is like this. So, in the now inside the wave guide there will be this wave will go and it comes back, there is a standing wave created. So, we measure that standing wave thing. Also, you can see the point contact diode detectors, etc., that is shown in this same figure. Now, the you see the tunable probe we have shown here. This is the field distribution of the detector, and finally, it is going to either your, so some the current we are sending from the voltage, we are the diode is converting that to the current, that current is going and to the VSWR meter. Now, measurement of unknown load impedance. Let us come to our basic point, measurement of unknown load impedance. So, the two things you need to know measurement of VSWR of the line. So, that means in that waveguide, depending on with which we have terminated, means if we go back to our actual diagrams, you see that at the end there is a termination we give, that is the load. what load we give, depending on the voltage standing wave pattern will be created inside the waveguide, and that VSWR means voltage standing wave ratio. I think you know from your transmission line theory that it is defined as voltage maximum by voltage minimum of the line. So, that depends on the mismatch. That means, if you have a transmission line with characteristic impedance Z0 and if the load is ZL, then depending on that there is a standing wave created. So, one parameter for measuring that is reflection coefficient, which we have seen. Reflection coefficient is Z2 or ZL minus Z0 by ZL plus Z0. But another criteria, that a scalar criteria from reflection coefficient. Reflection coefficient is a complex quantity, but a measurable quantity, scalar quantity from this is VSWR, which is defined as VSWR is V max by V min. That means, if we have a distribution, voltage is varying. So, the maximum to minimum, that is called VSWR. Also, it is related to the, we will see that this thing we need to measure from the line, and measurement of the minimum position, minimum shift in voltage minima for short and unknown load. So, this just to note, actually we will discuss what that mean. So, when we see the procedure of the thing. So, if we can see the voltage minima, what is the shift in that, in two cases. One is, if we put a short, we will note down the voltage minima position, then we will change that and put a unknown load which we are trying to measure, we will find out where is the minima, we will note down that position, that shift we are calling L min. So, if you know these two, you can find out the load impedance which is unknown. So, this first part, that means measurement of VSWR, that is done by the VSWR meter. In the microwave bench we have already seen VSWR meter, this is a better view of that. So, there are, you have all used it in your labs, you will see that there are various power knobs. So, by that you can connect an AC power or external power, etc. Then you can also find out the probe that you are connecting. So, depending on that probe, so that you can get proper impedance. So, there are input selector. So, there are 100K or 100 ohm, etc. That means, depending on your the diode contact probe, its impedance, you can change this point. Then you can see that number 3 is the input. That means, there you connect the through a BNC cable, you connect from that slotted carriage, the signal you can take it in input to this. Then you can change the frequency of operation. That means, we have seen that you are taking a 1 kilohertz signal. Now, that frequency you can slightly adjust by the frequency knob, which is number 6, and then number 7 is bandwidth of that signal. 1 kilohertz is the center frequency, but there you can play with the bandwidth also, but these are not more important, but more important are this range knob, that 8 and 9, by which you give that what are the in dB scale, how much what VSWR you are giving there. And another important thing is this 10 and 11, those are the gains. Suppose if you are not getting good amount of signal, so you can give this VSWR meter a gain. Actually, this VSWR meter is nothing but a tuned amplifier. Whatever voltage is coming, it is amplifying it and showing you, like a tuned amplifier sort of thing. And there is the display, and also number 12 is the that display. All displays, you know, that sometimes require a mechanical offset by thing, because when no signal is given, you will see some deflection. So, that needle, that spring needs some mechanical adjustment, that is number 12. Now, VSWR is measured by this VSWR meter. You can see whatever I said, that VSWR meter front panel. So, same what I have seen more or less, and you see that you can measure in that display what is the value of VSWR, and this is the VSWR meter display. You see the right hand side is the VSWR. I think you know that it can vary from 1 to infinity. If you have a matched load, then VSWR is 1. If you have an short or open, VSWR is infinity. So, 1 to infinity this scale, but at one go they are not giving that scale. So, the topmost one is 1 to 1.2 or 3 something they are giving. Then if you have more VSWR, you switch over to 1 to 4. If you have more, you can switch over to up to 10, etc. More than 10 generally we do not measure, though theoretically it can go up to infinity, but in that time there is no point, because that circuit is useless if you have so much out. Now, this I just ask you to refresh your transmission line thing, and in a this is transmission line stuff, that if we move along the transmission line, you can find out this, that you see any good transmission line theory book, and the voltage in the line, voltage means is total voltage, that means the incident voltage plus the reflected voltage, that is called the total voltage, that is given by this formula, that Vx, its magnitude, Vx is a phasor, its magnitude is 1 plus the load reflection coefficient e to the power minus j 2 beta x, where x is your distance from the load. Load is at x is equal to 0. So, you are at whatever x is equal to distance, then the denominator is 1 plus gamma L, and then the VL is the voltage at the load. You know that in a transmission line, if I move along the line from the load towards generator, then the whatever the voltage I am seeing at load, then everywhere the voltage is changing, that is called line voltage. So, everywhere the current is also changing, everywhere the impedance, line impedance is also changing, but in the whole game one also the reflection coefficient, line reflection coefficient also changes, but who is invariant? The invariant quantity is VSWR. That depends on the mismatch at the load, and this voltage will change, but Vmax by Vmin, this ratio of VSWR, that is invariant. So, if I move along the line, VSWR does not change. That is why if we can measure, we can find out what is the load. So, voltage will be maximum if you look at this, the variation along the line, that means the x variation is coming from the numerator only, that 1 plus gamma L e to the power minus j 2 beta x, that is the only variable thing, others are all constant, because load reflection coefficient is load thing. So, once I start moving, the variation is the upper one. So, maximum of that, you see two vectors or two vector quantities or two phasor quantities, one is 1 0, that means a real axis line, and another is gamma L e to the power minus j 2 beta x. So, actually gamma L, it is a complex number. So, we can call it as gamma L bar some angle that we are calling theta gamma L, and then you see that e to the power, that means I will get a 2 beta d. So, this 2 beta d or 2 beta, if I have a distance d. So, in the phasor diagram, this is called crank diagram, here we have shown that one is your 1 0 phasor, and then there is, it is summed with another phasor of the green one. So, the resultant is the this red one phasor. So, that is changing the maximum value of that when that red thing will fall on the real axis, that means will be collinear with 1 0. That means, when both this red and green they are collinear, you will get a voltage maxima. When they are collinear but opposite, that means the after another 180 degree rotation, that green one will be oppositely directed to one angle 0. So, that time we will get voltage minimum. So, voltage is maximum when those two are collinear and in same direction. So, now we can see that there will be voltage goes to maxima and minima if we move along the line. Minima occurs, as I said, when these two phasors are collinear, but opposite. So, you can do that, that means opposite means this theta gamma L minus 2 beta d, that should be having an angle pi. Then only they will be, the two phasors will be opposite. So, from this you can find out this theta L is pi plus 2 beta d, we are calling that d minimum. So, voltage goes through maxima and minima. Minima occurs, we have seen, and also we have seen that whole game will be if the phasor covers a full rotation on the any phasor rotating full means actually it is by a rotation of lambda g by 2, where lambda g is the guide wavelength along line. So, voltage minima repeats every lambda g by 2 along line. So, what is the maximum value for that? This V max, if you do now, that when they are collinear, if you put that value, it will come out that V max is this and V min is this. So, this ratio V max by V min, it is given by this. So, when we wrote earlier that VSWR is this thing, you see we have defined this. Now, we are finding that in any general transmission line, it is related to the reflection coefficient as 1 plus reflection coefficient's magnitude by 1 minus reflection coefficient's magnitude. So, you see that VSWR, which we said that it is constant along the line, it also is related to reflection coefficient. So, it is, as we know from our Smith chart knowledge, that so it is also related to the impedance. So, from this we can always find out the unknown impedance if we know VSWR, and it is a measurable quantity. So, that is there. So, what is done, that as I said, that first you put a short circuit as a termination. So, you see the upper graph, that from the, you know that if you put a short circuit there, the voltage will be 0. Then if you move along the line towards generator, it will go to maxima, minima, and that thing is from this crank diagram, it can be proved that you will have a variation like that. So, in the carriage of the microwave bench, you have this scale attached. So, from that you can find out what are the positions of the minima when I have connected short circuit. Then you remove short circuit and put an unknown load. Obviously, if this load is not short or open or anything, so it will also have the that standing wave pattern. Only thing is, at that position in a short circuit, at the position of the load you have a 0. If you have an open circuit, at the position of the load you have an infinite value of voltage maxima, but in an unknown load, in general load, you have something, it may be maxima, may be minima. So, it will be there, that you see we have the second graph is showing that how it looks like for an unknown load, but here also you can find out by moving your probe that what is the minima position, what is the maxima position, locate those minima. Now, to make VSWR measurement, you need to do a calibration. That calibration is, you first find out in when you have connected the load, what is the maximum voltage you are getting. Now, V max, now there are gain knobs and others in the VSWR meter. So, you make it adjust to 1. The moment you adjust to 1, then V minimum, that becomes 1 by S. You can see from here that when we have said this, that you see if I make V max 1, then basically V minima is becoming 1 by S. So, that is what we are writing, that V minima is 1 by S. Now, the VSWR meter scale is graduated in terms of this S. S stands for VSWR. So, from here you can measure that. So, this instrument helps you to measure VSWR. So, what you do, again I am repeating the procedure: pick VSWR meter by tuning your probe, move the probe along the line, locate voltage maximum, adjust gain and vernier knob of VSWR meter or output power to obtain a VSWR reading 1, move the probe along the line to a voltage minima. That means you are moving, your needle is on the VSWR meter display, it is moving left, and the point where you are getting minima, there note the VSWR values from scale, that is the VSWR of the line. So, this is shown here that how the voltage, the red colored one, voltage varies for a shorted one, how it varies for a open one, how it varies in the general case. This we have already seen. Now, a typical measurement scenario, suppose frequency of operation is 7.5 gigahertz, a short placed at load plane. Let us say we have done this experiment, let us say this is recording of one of the students you have measured. So, recorded when the short is placed at load plane, the scale minima positions he has noted like this: short removed and unknown load put, VSWR he measured by the method we said, let us say it is 1.5, voltage minima. Now, the voltage minima is shifted, so he has again found out this. So, now here one question, that why we not why we measured the minimas, we could have measured the maxima also, both of them repeats after a lambda g by 2, but you have seen that maxima, near that if you do the derivative of the curve, which is a sensitivity, for maxima it is 0, because near that curve the slope is 0. So, if you perform an experiment there and suppose you miss the maxima, the error committed will be it is very insensitive, the probe is there, whereas in place of minima the sensitivity, the slope is quite high, that is why the sensitivity of the measurement is good. So, that is why instead of maxima we always measure the minima points. So, because it is sharply defined, the voltage is at the maxima, it is flat, that is why it is not so sharply defined. So, let us continue that measurement. Voltage minima repeats every lambda by 2. So, we can find out by finding the difference between two minima position, we can calculate what is the lambda g. In this case it is coming out to be 4 centimeter. Now, consider, so let load be at 4.2 centimeter. Actually, load position is not accessible to you. You have seen that because in the carriage where the load is put, the scale is not there, but since everything is repeated, so you can find out any one as the minima. There are several minimas, any one you take. So, that is what we said, that let we take that load it at 4.2 centimeter. So, when we have changed that to unknown load, the nearest minima under load is at 2.72 centimeter. Only thing, from the curves I have shown, you will have to find out that whether it is that when it is getting changed, suppose this minima is changing, if I take this minima, you see that this minima is towards load, it is shifting. If I take this minima from there, it is towards generator. So, that you need to be careful in the measurement, that whether it is that so from this I have got that L mean, which is 1.48, I have noted it towards generator. Then here we are not taking the help of Smith chart, you can do these calculations, that so gamma magnitude, reflection coefficient magnitude is related to VSWR by this. This is the formula that we have seen, VSWR is equal to 1 plus gamma by 1 minus gamma. So, if you change the sides, gamma is equal to VSWR minus 1 by VSWR plus 1. By this you are getting this 0.2 is the reflection coefficient magnitude. Then theta you can find out, because beta means 2 pi by lambda. We have given frequency, from that you can find lambda, and we have seen that shift is 1.48 centimeter. So, angle wise it will come as 86.4 degree. Then gamma will be gamma magnitude into e to the power j 86.4 degree. So, that if you convert to rectangular things, it will be like this. So, you have got gamma. Now, ZL, the reflection coefficient is related. This is the basic relation of Smith chart. So, this is always true. So, what is the corresponding ZL? This is this. So, you can find out the unknown value of the impedance.